Hello, everyone, and welcome to your Thomas Tool Tuesday. For this week, we're going to be talking about the single most important chart in meteorology that you can look at. Before we do, though, a special thanks to Dr. Market for requesting this video. If you have a request for something you want me to go over in the future, please do let me know, and I'll be happy to make a video on it. This one's going to be a little different. This chart needs to be done justice, so I've made a far more structured presentation for it in this case. This is going to be more of an educational deep dive into how to interpret this chart rather than showing you a specific tool to pull one up. So let's begin. This is the 500 millibar chart. That's what we're going to be looking at today. Let's go over what it is. The 500 millibar chart is our best way of assessing the weather across the atmosphere, bar none. If there's only one chart you could look at in the atmosphere, this would be the chart to have. It's in the middle of the troposphere. That tends to be around the 16,000 to 20,000 foot mark, and it tends to be a constant pressure chart. That's exactly what it is. Here's why that matters. The reason is because instead of it showing you a constant height surface, it shows you a constant pressure surface. The depth of the troposphere changes. As you have cooler, more dense air, the troposphere shrinks. As you have warmer, less dense air, the troposphere expands. Regardless of the exact height of the midpoint of the troposphere, the 500 millibar map will do a pretty good job of capturing it. So instead of having to play guesswork, you now have a pretty good idea of what the middle of the troposphere looks like. So if you look at a surface pressure map, that classic one with the highs and lows, that tends to be a map where you're at the surface of the Earth and you have constant pressure lines with high and low pressure systems. In this case, it's reversed. We now have constant pressure as our surface with constant height lines now in place that tell you how high up in the atmosphere you are before you hit 500 millibars. So let's go over how to interpret this. This is a height map. It shows you the heights of different portions of the atmosphere when you hit 500 millibars. Here's how to interpret it. You'll notice those numbers on the lines: 576, 570, 558, 546. This is decameters. That's what you're looking at. So it shows you every 10 meters in the atmosphere is 1 decameter. So you just add a 0 to the end of the number you're looking at. That's how many meters up in the atmosphere you have to be before you hit 500 millibars. This is very important. The higher your heights are, generally, the warmer the column of air below, and generally the more stable your atmosphere. The lower your heights, the cooler the air is below, the more dense the air is below, and the less stable your atmosphere tends to be. So big picture, the 500 millibar chart, again, I can't go over it enough, the best overall chart for assessing the weather pattern. You can assess the weather pattern by looking for 3 major features. These are known as troughs, ridges, and shortwaves. Let's break it down. Starting with troughs, these are going to be the valleys in your map. Can you spot one? I can spot one. This is it. We've drawn the trough axis now. At the base of that trough, that's going to be important. Just keep an eye on it. That's going to be at the very bottom of that valley. Just pay attention to that. We're going to go over that in more detail. That's a feature that's very important in these troughs. But troughs are U-shaped dips and height lines. What they mean usually is that you have a cooler than usual weather pattern in place, and they're associated with instability. It can be a sign of precipitation. We usually have unsettled weather ahead of these troughs and improving weather behind them. Then we have ridges. These are the hills with N-shaped bumps in the height lines. Usually warmer than usual weather is associated with them. They're marked by zigzag lines, and they're usually associated with stability and can be a sign of fair weather conditions. Weather tends to improve ahead of ridges and be more unsettled behind them. Then we have short waves, and these are essentially just little kinks embedded within your larger troughs and ridges. What we just went over are known as long wave troughs and long wave ridges. Essentially, you just have mini versions of those that are embedded within. So if you have a shortwave trough like the one on this map near the center of your screen, usually ahead of those you're going to have instability, and that'll be the greatest chance for storms in the Midwest, especially in the spring and summer months. So your best storm chance is going to be to the east of a shortwave. So then we break it down in a little more detail. We've talked about everything you can get out of just the heights alone on a 500 millibar map, but there's more. When a meteorologist hears 500 millibars, they aren't usually thinking about heights. they're usually thinking about vorticity. This is because it measures the spin in our atmosphere, which allows us to assess where there's lift and sinking motion. There are two types of vorticity we'll go over today: positive vorticity, or counterclockwise vorticity, and negative vorticity, or clockwise vorticity. Now, there are three different variants of vorticity that create absolute vorticity, which is what we care about. There's curvature vorticity, which is the spin from wind shifts. Positive vorticity tends to be counterclockwise, negative vorticity clockwise. That's what we just went over. Then we have shear vorticity. This is spin from wind speed changing over a distance. Positive tends to be when winds increase with distance. Negative tends to be when winds decrease with distance. And finally, we have the earth vorticity, or the Coriolis force, spin that the air has from being on a spinning planet. Positive curvature, or earth vorticity, Coriolis vorticity, is from poleward motion, moving from the equator towards a pole. Negative earth vorticity is due to equatorward motion, or moving from a pole toward the equator. The formula is fairly simple here. Absolute vorticity is just the sum of the remainder of its parts. For our purposes, we care primarily about curvature vorticity, but shear and Coriolis vorticity aren't trivial either. So let's now go over what a vorticity map can tell you. Only positive vorticity tends to be shown on them, although on some websites like Pivotal Weather, which is a popular one amongst us here at Mizzou Meteorology, you may see some negative vorticity plots as well. An X on most maps denotes a vorticity maximum. Sometimes they're colored like this, sometimes they're colored red, sometimes they're colored yellow, depending on where you look. These are important. Notice that most of them are at the bases of troughs. This is going to be important in just a moment. Vorticity maximums can be used to forecast the trajectory of lift as well. If you see that the base of a trough and its associated vorticity maximum are moving into the Midwest, for example, you can bet that there's going to be lift in the Midwest. We call this positive vorticity advection. All it means is that we have positive vorticity moving horizontally. Advection is just a fancy way of saying horizontal motion. So the translation of positive vorticity into another area is also known as positive vorticity advection. So let's go over vorticity advection in a little more detail. Positive vorticity advection is the translation of positive vorticity into a new area. Here's why it matters. Positive vorticity advection tends to contribute to air spreading out aloft. This is known as divergence, leading to air at the surface rising to fill the vacuum that's created. The result is that rising air can create clouds, low pressure systems, and precipitation if the conditions are right. Negative vorticity advection is exactly what it sounds like. It's exactly the opposite of positive vorticity advection. Spin decreases, air sinks, weather generally improves. So when we put it all together, looking at a trough, behind the trough, weather tends to improve. Ahead of a trough, weather tends to deteriorate. Then if we look at a ridge, it's the opposite. Ahead of a ridge, weather is improving. Behind a ridge, weather tends to deteriorate. At the base of a trough, that's where we tend to see our vorticity maximums. The movement of those vorticity maximums can determine where we expect lift, and by extension, where weather is expected to deteriorate the most rapidly. So let's look at some basic patterns you might find on a 500 millibar chart. The first is an open wave pattern, far and away the most common pattern that you'll find when you open this. Again, same principles apply. Ahead of troughs, weather tends to be unsettled. Behind them, the weather tends to be better. The opposite is true for ridges. Keep an eye on these. These are important. There are two types of troughs that we want to go over here as well because they have implications. The weaker of the two tends to be the positively tilted trough. Unsettled weather ahead, and then behind we see that clearer weather. This tends to be a more widespread area of unsettled weather, but it doesn't tend to be super focused when it comes to where the energy lines up. So the intensity of unsettled weather tends to be a bit lower, but your overall widespread nature tends to be a bit more robust. Then you have negatively tilted troughs. Negatively tilted troughs, same rules apply. Ahead of the trough, weather is unsettled. Behind the trough, weather tends to improve. But negatively tilted troughs tend to have slightly less widespread regions of unsettled weather. The difference is that weather tends to be significantly more intense. So if you see a negatively tilted trough, that's when you can see severe weather, nor'easters. Now there are exceptions to these rules. You can get severe weather with positively tilted troughs and weaker systems otherwise. But a general rule of thumb is that a positively tilted trough is a less powerful but more widespread weather system than a negatively tilted trough. General rule of thumb to remember the two: a positively tilted trough, it has a positive axis, just like if you're looking at a graph, a positive slope. Negatively tilted troughs have a negative slope, like if you were looking at a graph as well. And it wouldn't be a good video if we didn't go over a few more of these patterns. The next being zonal flow. This is the boring one. This one is where you just have straight west to east flow. It tends to follow your latitude lines. It's named zonal flow because latitude lines in some places are called zones. So it's parallel to the zone. That's why it's called zonal flow. You tend to have a situation generally where your weather tends to be more unsettled to the west, less unsettled to the east, but overall you have a clash of air masses, the warm side to the south of the jet, the cool side to the north of the jet. That's what we generally expect in these zonal flow regimes, with short waves riding along them that can create more unsettled weather. We then have a cutoff low. These tend to be fairly unpredictable. These are low pressure systems that are detached from the main jet stream and can just sit there and linger in an area not controlled by any large scale flow for extended periods of time. These are particularly well known for causing flooding issues and being very difficult to predict, especially in the winter and springtime. It wouldn't be a good 500 millibar chart video if I didn't go over some blocking patterns. Dr. Lupo would be disappointed in me if I didn't go over them, so let's do it together. The most common of the blocking patterns is going to be your blocking high. This means that you're going to have a heat wave, usually to its east where your surface high pressure system resides. Fair weather across the high pressure system in general as well. The warmest weather, again, though, to the east, slightly cooler off to the west. This is the most common of the blocking patterns you'll see. Two more to go. The next is the omega block. More mild weather within the high pressure system, the ridge. The troughs tend to have cooler, more unsettled weather, but essentially it makes the omega Greek letter. You have two troughs that are wedging a ridge in between, making it very difficult for that ridge to move, meaning that this can be stuck in place, a pattern like this, for weeks at times in extreme scenarios before that omega pattern starts to break down. This has been famous for creating some intense heat waves over the summer at times. The final blocking pattern is the Rex block. A high pressure system is trapped north of a low pressure system, so you actually have a warmer air mass to the north of a cooler air mass. This tends to create a blocking pattern where you have more unsettled weather to the south, more mild weather to the north. Then out ahead of that pattern, it tends to shoot out some short waves that can create disturbances in a more zonal flow regime like the one shown in the eastern portions of this image. So with that, thank you so much for watching this video. I know this one was longer, it was a bit more sciencey than usual, but I felt the need to do the 500 millibar chart justice. I hope this was enjoyable. If you have any requests for me for next week, please feel free to let me know. I'm not sure what the topic for next week looks like just yet, so don't be afraid to make a request. We haven't even mentioned what winds look like at 500 millibars yet, so if you want a part 2 to this video, or want me to go over something else, please let me know. With that being said, thank you so much for watching. I'll see you next Tuesday.